Hi everyone, I'm Sidharth Gupta. Today I'm going to be talking about a method for efficiently training deep neural networks to be robust against adversarial test samples. And this is joint work with Parijat, Dube, and Ashish Verma at IBM Research. I think by now some of us know that deep neural networks can be sensitive to imperceptible perturbations in their test data. For example, in the top row we have original test images from the CVPR10 image dataset. In the bottom row, we have the same images perturbed by a very small amount that is almost imperceptible to the human eye. If I train a deep neural network to classify CFAR10 images, all the images in the top row are correctly classified. However, the images in the bottom row are all incorrectly classified when tested with the same model. This is amazing because us humans would not classify the bottom row incorrectly at all. It has been known for some time that deep neural networks suffer from this problem, and there have been a variety of approaches to train models to be robust against such adversarial samples. One popular method is regular adversarial training, or adversarial training, where we seek to solve the optimization problem shown here. Script L is the loss function, F theta is a deep neural network that is parameterized by parameters theta, and X is a training sample, and Y is the actual class of that training sample. For each training sample, we try and replace it with an adversarial counterpart that maximizes the loss. And then we minimize the neural network's parameters on these adversarial samples rather than the samples of the original training dataset. To do this maximization, we use projected gradient descent, where we are really doing gradient ascent instead on the loss function. After each iteration of gradient descent, we project the result to be within an epsilon ball around the true sample so that it still resembles the original sample. Now, the thing to note here with projected gradient descent is that during training, we will see the original training sample multiple times in different mini batches and different training epochs. However, because this projected gradient descent method depends on the parameters theta of the neural network, and these are constantly evolving, every time a training sample arrives, the parameters will be different, and therefore we cannot use the same adversarial counterpart for a training sample, and we will have to regenerate the adversarial sample each time. And so we will have to run this projected gradient descent method each time a sample comes, even if we've seen this sample before during training. And because projected gradient descent requires gradients, we have to do multiple forward and backward passes of the deep neural network, depending on the number of PGD iterations that we wish to do in order to regenerate these adversarial samples. And the larger the network is, the more time consuming this projected gradient descent method can be. So in total, we expect regular adversarial training to take significantly longer than natural training. This table here compares the training time taken to perform natural and regular adversarial training with the CVPR10 dataset with two popular deep neural network architectures. As expected, regular adversarial training takes significantly longer. The goal of this work is to reduce the time taken for adversarial training, but still get performance on natural and adversarial samples that is comparable to regular adversarial training. So as we just saw, the generated adversarial samples depend on the evolving model parameters. And initially, these parameters are randomly initialized, and so they are often very different from the parameters of the final model. As a consequence, the adversarial training samples generated for use at the start of training are very different to the kind of adversarial samples that will be used at the end of training and during test time once this model is deployed. However, we still generate these adversarial samples from the start of training during regular adversarial training, and this requires us to do projected gradient descent right from the start, and this increases the training time. We can verify the usefulness of the initial adversarial samples through a simple experiment. We're going to perform regular adversarial training on a wide ResNet with the CVPR10 dataset, and we are also going to save the model's parameters every 5 epochs. Next, we test the final model with adversaries generated using the model's parameters from previous epochs. The blue curve plots the accuracy of when the test data is generated using parameters from previous epochs. There is a decrease after epoch 100 because of a learning rate reduction. However, we can see that for the first part, accuracy is significantly higher than the adversarial accuracy of the model at the end. This suggests that adversarial samples in the initial phase of training are not really helping to build robustness in the way that we may have wanted. So after realizing that adversarial samples in the initial phase of training may not help build robustness, we thought of a new method which we are going to call delayed adversarial training that can help us handle this long-standing problem of the large amount of training time taken for regular adversarial training. So we propose to replace the adversarial samples in the initial phase of training with some other samples until the model stabilizes and reaches a phase where adversarial samples can be useful. In this work, we decide to use natural samples because they are really free and there's no time taken to generate them because we already have them and they're already available. Furthermore, we would want our final perform to anyway perform well on natural samples, and in regular adversarial training, the model may never actually see natural samples. We perform a simple experiment to verify whether this is a promising direction that gives us suitable performance on clean and adversarial test samples. The blue curves on both the left and right plots show the test accuracy when regular adversarial training is used. We have natural accuracy on the left and adversarial accuracy on the right. The training and testing adversary strengths are the same. We also have some switching curves where switches are made at different epochs. A switch is the epoch at which we switch from using natural samples to using adversarial samples during training. We see that there is a wide range of epochs where we can perform the switch and get comparable or actually in some cases even better performance as compared to regular adversarial training. We also observe that we should not switch too late after the learning rate drop at epoch 100 because the learning rate drop is an external action that encourages the model to converge further. By switching to adversarial samples during training, we have reduced training time by using natural samples at the start. We build upon this by coming up with an automated switching method. We noticed that in the initial phase of training, we are training with natural samples, and during this phase, the training loss in natural samples stabilizes before the first learning rate drop between epochs 55 to 85. This means that the model parameters are stabilizing during this period, and we can detect when the stabilization is happening and automatically perform the switch from natural to adversarial training samples during this period between epoch 55 and 85. Do check out our full paper for more details on how exactly we perform this switch. Our method proposed yet delayed adversarial training is attractive because it does not require multiple initial training runs to determine when to perform the switch. We can do this at runtime. Furthermore, we propose to use natural training samples which we already have, and so it is straightforward to integrate into an existing robustness training pipeline. Let's take a look at these curves which I showed in the previous slide a little more closely. We can see that the final accuracy obtained with delayed adversarial training is higher than the final accuracy obtained with regular adversarial training in many of the instances where delayed adversarial training has been used. A similar observation has been made in other works that were being done by other researchers around the same time as we were doing this work. Those researchers instead used weaker strength adversary samples in the initial phases of training and found that this helps accuracy too. We, however, here, rather than using weaker strength adversaries, are using natural training samples. When using delayed adversarial training, the models are not all fitting to adversarial samples of little relevance in the initial phase of training. Instead, they are fitting to natural samples which need to be classified correctly. In our paper, we also compared the training loss curves of regular adversarial training and delayed adversarial training. We observe a high training loss when our method is used. This, along with the higher accuracy, indicates better generalization. Let us now take a look at some experimental results. First, let's see how delayed adversarial training performs compared to regular adversarial training for a variety of different model architectures and datasets. On this slide, the adversarial samples used during training and test are of the same strength. First, we check CVPR10 with the wide ResNet 2810. We see that we are getting over 60% time saving when using our method. Our method also gives us the highest accuracy. Please do check our full paper for how we perform early stopping here. For ResNet 18, we get a similar outcome. There is a significant time saving of over 50% and a gain in adversarial accuracy when using our method. We further see that these patterns extend to different datasets such as CVPR 100 and MNIST, which are also using different model architectures. Next, we investigate how our method performs when the models trained during delayed adversarial training are tested against adversaries of a different strength to the training adversary strength. In other words, we keep the projected gradient descent epsilon ball size fixed and vary the number of steps, or we keep the number of steps fixed and vary the epsilon ball size. Over here, we see that delayed adversarial training gives curves which are very similar to regular adversarial training, which indicates that the generalization performance of regular adversarial training is matched despite us using adversarial samples much later on in the training process. In fact, as we discussed earlier, in some cases, delayed adversarial training gives a higher accuracy. So these curves are with CVPR10 and the wide ResNet 2810. We can also see what happens with the ResNet 18. With a ResNet 18 and CVPR10, we see the same trend. And with MNIST and a 2-layer CNN, we get curves like this instead. Again, we see that delayed adversarial training follows the curves of regular adversarial training very closely. However, MNIST has this very characteristic drop in accuracy when tested using an epsilon ball larger than the one used in training, as has also been noted in other works. We're able to push this drop further, and during this period of steep descent, we can get extremely large performance benefits when using delayed adversarial training. We also verified the black box performance of our method. We generate adversarial test samples from independently trained copies of the network. In this case, we use CVPR10 with the wide ResNet 2810. The independent network copies are trained using natural training, regular adversarial training, and delayed adversarial training. And as is consistent with the literature, the adversaries generated from independent copies of the network are misclassified less often, and the adversaries from the naturally trained independent copy have the highest accuracy. So in summary, there is an initial phase of regular adversarial training where adversarial training samples do not help robustness. Yet we normally generate adversarial samples in this period, which takes time and increases the total training time. Instead, we have developed an adversarial training procedure which uses natural samples in the initial phase of training and so significantly reduces the training time because we no longer need to use adversarial samples from the beginning of training. Furthermore, through extensive experiments, we demonstrate that the test accuracy does not suffer using our delayed adversarial training method either. Please do check out our full paper for more details and more experimental results.